Now that we know what is required for a chemical reaction to occur, we actually have to have our molecules colliding. Number one, they have to collide. Number one, they have to collide. Number two, they have to collide with enough energy. And number three, they have to collide in the right orientation for the atoms to rearrange in space. What can we do now to help reactants over the activation energy and speed up the reaction? Let's think about you in the hallway. If it's during class time, um, there are fewer people in the hallway, but in between class times, there's more people in the hallway. Are you more likely to run into people during class or in between classes? In between classes, because there are more people in the hallway, and it's more likely for you to bump into someone in a crowded hallway than it is in a hallway that's not crowded. What else can you do to ensure that you would have a collision and drop all your books? Because you could have a collision, but you don't drop all your books. Remember, the reaction is you having a collision and dropping all your books. Well, you could actually have, if you're running now, even if it's just one person in the hallway, if you're running and you're not paying attention, you could run into somebody and a reaction will occur because you're adding more energy to the system. What if someone pushes you or they trip you? You're walking down the hallway and someone trips you now and you bump into someone and you drop your books. What do all of those represent? Well, changes in temperature would be like you running down the hallway. You have more energy and you're able to run into someone and bump into them with greater force, right? Changing in concentration is that during classes, there aren't many people in the hallway, but after class, in between classes, there are plenty of people in the hallway, a lot more opportunity for you to actually have a collision, right? If someone's to push you or trip you, that gives you another way in which you bump into someone and drop your books. So someone tripping you would be like adding a catalyst. So let's go back to our simulation right quick. And let's reset our, let's go into a many collisions. And let's put in, we're going to start off with one of each molecule. Notice that we don't have enough molecules for our reaction to occur. But let's raise our temperature enough that we are actually at or above our activation energy, right? Let's add some more molecules. Notice that if once I start adding more molecules, I end up getting more products, right? I add more products. I'm already over the activation energy. So if I add more reactants, I'm going to get more products, right? Add more reactants, I get more products, right? Let's clear our container. Let's reset everything and start it cold. And I'm going to add 15 molecules of each. So we've seen already what can happen when we have enough energy and we add more molecules, the reaction will occur faster, right? Now let's say we have plenty of molecules and let's see what happens when we raise the temperature. Notice that I start getting some molecules going to products. That's because this is an average energy and this is the average total energy, and Some molecules can have more energy than others. Okay? But if we continue to raise the temperature over the activation energy, notice that we're going to have many more collisions that occur and we get more products. Notice how at some point we get stability and there's no change in the reactants and the products. Boom, boom. Oh, I shouldn't say boom, sorry. Right there, right there, right there. When those concentrations remain constant for a moment, we hit equilibrium. And so notice that I can form reactants and form products at the same time. We're going to come back to that. So what are the two things that we looked at? So if I decrease the temperature now, notice that I'm not making any more, I'm not making much more product as fast as I was before. But if I raise the temperature, notice that I'm getting more product at a faster rate, right? And I still end up having these constants so often, okay? So temperature is going to affect the rate, all right? So at higher temperatures, I increase the kinetic energy of the molecules, making them move faster. If they move faster, they collide more often, and they're colliding more often with more energy. So I increase the frequency of collisions and the forcefulness of those collisions. So higher temperatures generally are going to increase the rate. Lower temperatures are going to decrease the rate of most chemical reactions. If I add more molecules, if I increase the reactant concentration, then that's going to give me more molecules and more possible collisions. All right, and the reactions go faster because I have more possible collisions. Now, a catalyst, all it does is speed up the rate of the reaction. So remember in our example of you bumping into someone and dropping your books in the hallway, if someone pushes you or if someone trips you, that provides another way for you to drop your books in the hallway, right? And you bump into someone and drop your books. So a catalyst just speeds up the rate of the reaction and it provides an alternate pathway. So the first pathway for you dropping your books was that you had to run into someone with enough speed and you drop your books. But a catalyst is someone pushing you, someone tripping you. Now you bump into someone automatically, right? It's a different way in which the reaction occurred. So what do we see a catalyst does? All it does is decreases the activation energy and provide another way for the reaction to occur. So here we have what kind of reaction? An endothermic reaction, and our activation is decreased by the addition of a catalyst. All right. Here we have an exothermic reaction, and notice that by adding a catalyst, we are going to decrease the activation energy. So what are the factors that increase the rate of a reaction? If I increase the temperature, I end up having more collisions with the correct amount of energy. And more collisions means that more likelihood that I'm going to have collisions in the right orientation. If I increase the reactant concentrations, I am adding more molecules in the system. So more molecules, more likely that they're going to bump into each other more often. Adding a catalyst now just simply lowers the activation energy to allow for reaction to react much faster. Now, I know that I'm saying molecules, but we're talking about any type of chemical reaction here, including those with aqueous solutions, aqueous ionic solutions. So let's practice and state the effect of each of these changes on the rate of a reaction. If I decrease the temperature of a reaction, I'm removing some energy. What will happen to the rate of the reaction? Will it increase, decrease, or have no change? Correct. It would decrease because I am removing some energy. And remember, we've got to get up over the activation energy. And if I decrease the energy that I supply to the system, I'm going to decrease the rate at which this occurs. All right, what if I take away one of the reactants, remove a reactant? Well, if I have no reactants, then I can't have a chemical reaction. So it's going to decrease the rate of the reaction. What about adding a catalyst? Adding a catalyst is going to increase the reaction. Remember when we talked about your rusty bike and water? What do you think water is, since if it rains, um, it rusts faster? Have you ever used a steel wool to clean your pots and pans? And as long as the steel wool stays dry, it doesn't get rusty. But as soon as it sits around and it gets moist and it stays wet, it gets rusty. So what can we say water is for the reaction between iron and oxygen to form rust? It's a catalyst. All right, back to the problems. If I put a reaction flask on ice, I'm essentially decreasing the temperature. So what would happen to the reaction rate? Correct. It is going to decrease the rate. And what if I increase the concentration of a reactant? That is going to increase the rate of a reaction.